Welcome to the deep dive. Today, we're not just dipping our toes, we're plunging into the very bedrock of inorganic chemistry.
That's right.
We're taking on the fundamental concepts from Part 1 Foundations of Shriver and Atkins Inorganic Chemistry, 5th edition.
A classic text.
Absolutely. And our mission here isn't just to list facts, it's to unearth those really potent insights.
And core ideas.
Exactly, those crucial nuggets of knowledge that genuinely transform how you understand the chemical world around you.
That's right. Because you should think of these foundational concepts not as like rules to memorize, but more as the essential lenses.
Lenses, okay.
Yeah, the lenses through which you'll interpret everything else in inorganic chemistry. They give you the framework, the underlying logic.
Right.
Once you really grasp the complex world of elements and compounds, it starts to make this kind of elegant sense. We're aiming for clarity, yeah, but also connection.
And those aha moments.
Definitely aiming for those satisfying aha moments.
Okay, so our goal for this deep dive is really to cut through all the detail, pull out the most important ideas from these early chapters. We want to give you, the listener, a clear, step-by-step understanding.
Make it accessible.
Yeah, accessible, maybe with a few surprising facts, maybe just enough humor to keep you hooked, so you can quickly get really well informed on this fundamental subject.
And it's important to say this isn't just a summary, right?
Well done at all.
Consider it more like a guided tour, maybe, helping you connect the dots to really understand why these principles matter so much. Foster that deep understanding that makes learning chemistry actually, well, rewarding.
Okay, let's start the tour. Where better to begin than the smallest building block?
Yeah.
The atom itself.
The very beginning.
We know the universe kicked off with mostly hydrogen and helium, the lightest elements. So the big question is, how did we end up with everything else? All the heavier stuff.
Yeah, and what's the deal with iron 56? You mentioned it in the outline.
Exactly. What's its cosmic secret?
Well, it's fascinating. The universe's first chemists were actually the stars.
Element factories.
Pretty much. Through a process called nucleosynthesis, lighter elements, everything up to iron, were forged in these incredibly hot, dense stellar cores.
Okay.
And the key insight, the reason iron is special, is that iron 56 has the most stable nucleus of all, period.
Most stable. How so?
It comes down to binding energy, basically, how tightly the protons and neutrons are held together. Iron 56 is at the peak. So making it is favorable, but breaking it apart or fusing it further actually costs energy in a star.
Ah, so stars naturally stop producing elements at iron.
Under normal circumstances, yes. To get elements heavier than iron, gold, lead, uranium, you need even more extreme conditions. You need catastrophic events.
Like supernovae.
Exactly. Those massive stellar explosions provide the sheer energy needed to synthesize the heavier elements. That's why things like gold or platinum are so much rarer than carbon or oxygen or iron. It tells a story about cosmic history.
That's a fantastic perspective. From cosmic factories down to the subatomic. Let's zoom in on the electrons within an atom, because for us chemists, their behavior is, well, it's almost everything.
It dictates the chemistry, yeah.
So what's the biggest hurdle, the biggest shift from thinking about, say, planets orbiting a sun to how electrons actually exist in an atom?
The absolute biggest shift is embracing quantum mechanics. You have to throw out the classical picture.
Right.
Louis de Broglie gave us wave-particle duality. Electrons aren't just tiny balls, they also act like waves.
Weird, but okay.
And that directly leads to Heisenberg's uncertainty principle, which means, fundamentally, we cannot know an electron's precise momentum and its exact position at the same time.
So no neat little orbit.
No neat orbits. It forces us to think differently.
So if we can't pinpoint them, how do we even describe where electrons are? What language do we use?
That's where Erwin Schrödinger comes in. His famous equation gives us mathematical descriptions called wave functions, symbolized by psi usually.
Okay, wave functions. What do they tell us?
They tell us about the electron's energy and its probable location. Crucially, the probability of finding an electron in a particular region of space is related to the square of its wave function.
Probability zones, not fixed paths.
Exactly. Think clouds of probability. And these wave functions, they have distinct features, almost like shapes or characteristics, that are absolutely vital for understanding chemical bonding.
You mentioned nodes before. Are those important features?
Hugely important. Wave functions have regions of positive and negative amplitude, think peaks and troughs of a wave. How these overlap determines bonding, and yes, they have nodes.
Places the electron definitely isn't.
Precisely. regions where the wave function and thus the probability goes to zero. Understanding these nodes, both radial, dealing with distance, and angular, dealing with shape and direction, is key to understanding orbital shapes like S, P, D, F, and how they interact.
Okay. And knowing a third orbital has 0 radial nodes tells us something specific.
It tells us it's the first time d orbitals appear at that energy level, Na3. The number of radial nodes generally increases as you go up in energy for the same orbital type, like 1s, 2s, 3s.
Got it. So, with all these quantum rules, how do we then systematically fill up these electron slots, these orbitals, in atoms with lots of electrons? This must be how the periodic table gets its structure.
Absolutely. For multi-electron atoms, we need a few more guiding principles, sort of the rules of the game.
Okay, lay them on me.
First, the Pauli exclusion principle. It's fundamental. No two electrons in an atom can have the exact same set of 4 quantum numbers, n, l, m, l, and m's.
The electron's unique address.
Kind of, yeah. The practical outcome is that any single orbital can hold a maximum of 2 electrons, and if it does, their spins must be opposite, one spin up, one spin down.
Paired spins. Okay, what else?
Then there's the Aufbau principle, which is German for building up. It generally guides the filling order lowest energy orbitals first. And Hund's rule is also key.
Hund's rule. Fill the bus seat singly first.
Huh, that's a great analogy. Yes, for orbitals of the same energy, like the 3p orbitals, electrons will go into separate orbitals with parallel spins before they start pairing up. Maximizes spin multiplicity.
And all these rules together explain the electron configurations.
They do. We also need to consider things like shielding, how inner electrons block the nuclear charge from outer electrons, and penetration, how some outer orbitals can sneak closer to the nucleus. This explains, for example, why a 2s orbital is lower in energy than a 2p in multi-electron atoms, which isn't true for hydrogen.
Okay, so these quantum rules and filling principles directly lead to the patterns, the trends we see across the periodic table.
Exactly. Elements fall into blocks, SPDF, and groups with similar properties because they have similar valence electron configurations. We see trends in size, ionization energy, electron affinity.
You mentioned one surprising trend earlier, the lanthanide contraction. Can you unpack that a bit?
Sure. So as you go across the periodic table, you eventually get to the lanthanide elements where the 4f orbitals are being filled.
Right down at the bottom, usually.
Yeah. Now, these orbitals are, they're quite diffuse, and they're really bad at shielding the outermost electrons from the increasing positive charge of the nucleus.
Poor shields.
Very poor shields. So the effective nuclear charge felt by the valence electrons increases more than you'd expect. The result is that the atoms actually shrink more than usual across the lanthanides, and this shrinkage carries over to the elements after the lanthanides in the D block.
So elements like hafnium are smaller than expected.
Exactly. Hafnium ends up being almost the same size as zirconium, which is right above it, even though it has way more protons and electrons. This lanthanide contraction has major consequences for the chemistry of those later elements. Density, reactivity, all sorts of things.
That's a fantastic example of a subtle quantum effect with big downstream consequences. Okay, what about ionization energy and electron affinity? Removing and adding electrons.
Right. Ionization energy is the energy needed to remove an electron. It generally increases across a period and decreases down a group. But there are big jumps.
Like when you try to remove a core electron.
Precisely. Look at lithium. Removing the first electron is easy. Removing the second one, that takes way more energy because you're breaking into a stable, closed shell.
And electron affinity. Adding an electron.
That's the energy change, usually released when an atom gains an electron in the gas phase. Trends are a bit messier, but halogens, for instance, have high electron affinities. They really want that extra electron to complete their octet.
You mentioned nitrogen having a low affinity, which seems odd for a non-metal.
Yeah, it's counterintuitive. Nitrogen has a half-filled ape subshell, which is relatively stable. Adding another electron means pairing it up in an orbital that already has one electron. That electron repulsion costs energy, making the process less favorable, sometimes even requiring energy input.
And electronegativity ties into this.
Electronegativity, often using the Pauling scale, is a measure of an atom's power to attract electrons within a chemical bond. It's not quite the same as electron affinity, but related. It helps us predict bond polarity. Is the bond mostly covalent, polar covalent, or ionic?
Super important concept. Okay, let's move up a level. From atoms to how they connect. Molecules? Shapes are critical. How do we predict molecular geometry?
The go-to starting point is the valence shell electron pair repulsion model. VSEPR.
VSEPR. Sounds complicated, but isn't the idea fairly simple?
The core idea is incredibly simple, yes. It just says that regions of high electron density around a central atom, whether they're bonding pairs or lone pairs, will arrange themselves in 3D space to be as far apart as possible to minimize electrostatic repulsion.
Minimize repulsion, maximize distance.
That's the essence. So 2 regions give linear, 3 give trigonal planar, 4 give tetrahedral, and so on. The key insight, though, is how it treats lone pairs.
They take up more space.
Exactly. Because a lone pair is only held by one nucleus, its electron cloud is sort of fatter and squatter. It repels bonding pairs more strongly than bonding pairs repel each other. This causes distortions from the ideal geometries.
Like in water. The HOH angle isn't the perfect tetrahedral 109.5 degrees.
Precisely. The 2 lone pairs on oxygen push the OH bonds closer together, giving an angle around 104.5 degrees. VSEPR predicts that bent shape beautifully. Or take SF4.
Sulfur tetrafluoride. 4 bonds, 1 lone pair, 5 regions total.
Right. 5 regions suggests a trigonal bipyramidal electron arrangement. But where does the lone pair go? VSEPR predicts it goes into one of the equatorial positions, the belt positions, not the axial ones.
Why equatorial?
Because that position minimizes repulsions more effectively. It only has 2 close neighbors at 90 degrees, whereas an axial lone pair would have 3. The result is a seesaw molecular shape. It's remarkably predictive for main group compounds.
So electron repulsion is the architect. But let's bring quantum mechanics back in. We have valence bond theory and molecular orbital theory to describe the bonds themselves.
Right. 2 different quantum perspectives on bonding.
Let's start with valence bond, VB theory. What's its approach?
VB theory thinks about bonds forming from the overlap of atomic orbitals on adjacent atoms. You get sigma bonds from head-on overlap, giving cylindrical symmetry around the bond axis.
Like in H2, the 2 1s orbitals overlap.
Exactly. And you get pi bonds from sideways overlap of p orbitals, like in double or triple bonds. N2 has 1 sigma and 2 pi bonds.
Okay. But what about molecules like methane, CH4? Carbon only has 2 unpaired electrons in its ground state, but forms 4 bonds.
Ah, that's where VB theory introduces hybridization. To explain methane's tetrahedral shape and 4 identical CH bonds, VB theory proposes that carbon's 2s and 3 2p orbitals mix, or hybridize, to form 4 equivalent sp3 hybrid orbitals, perfectly pointed towards the corners of a tetrahedron.
A mathematical mixing to match reality?
Pretty much. It gives us sp2 hybridization for trigonal planar shapes like ethene, and SLIPE for linear shapes like acetylene. It's very intuitive for visualizing localized bonds, though there's some debate about invoking d-orbital hybridization for hypervalent compounds like PCl5.
Okay, so VB is good for localized bonds and shapes via hybridization. How does molecular orbital MO theory differ?
MO theory takes a more holistic or delocalized view. It says when atoms come together, their atomic orbitals combine to form completely new molecular orbitals that span the entire molecule.
So electrons aren't owned by specific atoms or bonds anymore.
Not in the same way. They occupy these molecular orbitals, which can be bonding, lower energy, stabilizing, anti-bonding, higher energy, destabilizing, or sometimes non-bonding. You fill these MOs with the molecule's total valence electrons, following Pauli and Hund's rules again.
What's the big advantage of MO theory?
Its key insight is explaining things VB struggles with, like the paramagnetism of oxygen, O2. Lewis structures and simple VB predict it should be diamagnetic, no unpaired electrons. But MO theory correctly shows it has 2 unpaired electrons in degenerate pi antibonding orbital.
Ah, a major success.
Huge. MO theory also gives us a formal definition of bond order, half the difference between the number of electrons in bonding MOs and antibonding MOs.
So bond order 3 for N2 makes sense.
Yes, it correlates directly with its very strong triple bond and short bond length. A bond order of 0 means the molecule is unstable and won't form. MO diagrams showing the energy levels of the MOs are really powerful tools.
And these MO diagrams can look different for different molecules.
Oh, yes. For homonuclear diatomics, like N2 versus O2 or F2, there's actually a switch in the energy ordering of the sigma and pi MOs formed from the 2p atomic orbitals due to sp mixing effects.
Interesting detail. What about heteronuclear diatomics like CO or HF, different atoms?
In those cases, the atomic orbitals start at different energies. The resulting molecular orbitals are often skewed, meaning they're concentrated more on one atom than the other. In HF, for instance, the bonding MO is mostly located on the more electronegative fluorine atom.
Reflecting the bond polarity.
Exactly. MO theory handles polarity naturally, and there are even ways to use MO diagrams, like Walsh diagrams, to predict molecular shapes by seeing how orbital energies change with geometry.
Wow, okay, so two powerful but different ways to think about bonding. Now let's pivot to the macroscopic world of solids. How do atoms arrange themselves in solid materials?
Most inorganic solids aren't just random jumbles, they have long-range order. We describe this using the concept of a crystal lattice and a unit cell.
The unit cell being the smallest repeating bit.
Precisely. The smallest block you can stack together perfectly to build the entire crystal. Common types are primitive cubic, body-centered cubic, BCC, and face-centered cubic, FCC.
And metals often pack very efficiently.
Very efficiently. Many adopt structures called hexagonal close-packed, HCP, or cubic close-packed, CCP, which is actually the same as FCC. In these arrangements, atoms fill about 74% of the space, which is the maximum possible for identical spheres. Each atom touches 12 neighbors.
Maximum density packing. And this creates gaps or holes.
Exactly. Even in the tightest packing, there's still space left over. These spaces, or interstices, or holes, are crucial. In close-packed structures, there are two main types: smaller tetrahedral holes and larger octahedral holes.
And there's a fixed ratio.
Yes. For every sphere in the close-packed array, there's one octahedral hole and two tetrahedral holes. So the ratio is one sphere, one octahedral hole, two tetrahedral holes. This is key for ionic solids.
Oh, so how does this apply to salts like NaCl?
Well, in many simple ionic solids, you can think of the larger ions, usually the anions like Cl, forming a close-packed array, FCC in NaCl's case. The smaller cations, like Na plus As, then fit into some or all of the holes.
Which holes do the Na plus ions occupy in NaCl?
In the rock salt structure, the Na plus ions occupy all of the octahedral holes within the FCC array of Cl ions. This gives the correct 1.1 stoichiometry and explains the coordination number of 6 for both ions.
And other structures fill holes differently.
Yes. For example, in the zinc blende structure, ZNS, the S2 ions form an FCC array, and the Zn2 plus ions occupy half of the tetrahedral holes. Cesium chloride, CSEl, has a different non-close-packed structure. Perovskite, like KDO3, and spinel, like MgL2O4, are more complex but still based on filling interstitial sites in an oxide lattice.
Can we predict which structure will form?
We can get a rough idea using the ratio of the cation radius to the anion radius. Different ranges of this ratio tend to favor different coordination numbers and thus different structure types, but it's just a guideline.
Not foolproof.
No. Other factors like electronegativity differences and polarizability matter too. People create structure maps that plot compounds based on multiple parameters to get better predictions.
Okay, structure is one thing. What about the energy holding these ionic solids together? It must be strong.
Immensely strong. It's quantified by the lattice enthalpy, the energy released when 1 mole of the solid is formed from its gaseous ions. It's a measure of the ionic bond strength in the solid state.
How do we measure or calculate that?
Experimentally, we can use a Born-Haber cycle, which cleverly combines other measurable enthalpy changes, like ionization energy, electron affinity, atomization enthalpies, using Hess's law to find the lattice enthalpy indirectly.
A thermodynamic cycle.
Exactly. Theoretically, we can estimate it using equations like the Born-Mayer equation. This considers the electrostatic attractions between positive and negative ions, the repulsions between electron clouds, and gets quite sophisticated, even including van der Waals forces.
And this lattice enthalpy, does it explain properties we can observe?
Absolutely. It's crucial for understanding stability. For example, why do some metal carbonates decompose at lower temperatures than others? It often relates to lattice enthalpies. Higher charge density on the Clige curation can stabilize the oxide product more, favoring decomposition.
Interesting. What about solubility?
Solubility is a balance between lattice enthalpy, holding the solid together, and solvation enthalpy, ions interacting with the solvent. Salts, where the ions have very different sizes, often have a less favorable lattice enthalpy compared to their solvation, making them more soluble.
So it explains real chemical behavior.
Definitely. It also helps explain why certain small, highly charged anions, like fluoride F, are particularly good at stabilizing metals in unusually high oxidation states. They form very strong lattices.
Are crystals always perfect? Any flaws?
Oh, never perfectly perfect. Real crystals always contain defects. Point defects are common, like Schottky defects, where you have a pair of misunication and anion vacancies, maintaining charge balance.
Missing ions.
Right, or Frankel defects, where an ion leaves its normal lattice site and hops into an interstitial site, a hole where it shouldn't be. These defects are crucial for ion mobility in solids and can lead to non-stoichiometry.
Non-stoichiometry, meaning that the formula isn't exact.
Exactly. Like iron 2 oxide, which is often written FeO, but its actual composition is usually something like Fe1XO because some Fe2 plus sites are vacant, with charge compensated by some F3 plus ions. These defects control properties,
Including electrical properties. How do solids conduct electricity or not?
that brings us to band theory. In a solid, the vast number of atomic orbitals overlap and merge to form continuous bands of allowed electron energy levels separated by forbidden energy gaps.
Protons and gaps.
Right. In metals, the highest occupied band, the valence band, is only partially filled, or it overlaps with an empty band, the conduction band. This means electrons can easily move into slightly higher energy states and travel through the material when you apply a voltage. They're conductive.
And insulators.
Insulators have a completely filled valence band and a very large energy gap separating it from the empty conduction band. Electrons just can't easily jump that gap.
So semiconductors are in between.
Precisely. Semiconductors have a smaller band gap. Thermal energy can excite some electrons across the gap, allowing some conductivity. Crucially, we can tune this conductivity by doping.
Adding impurities.
Yes, adding an element with more valence electrons, like arsenic to silicon, creates extra electrons near the conduction band that's N-type doping. Adding an element with fewer valence electrons, like boron to silicon, creates holes, missing electrons, in the valence band, allowing electron movement that's P-type doping. This control is the basis of all modern electronics.
Fantastic. Okay, let's switch gears to reactions. Two huge categories: acids, bases, and redox. Let's tackle acids and bases first. We usually start with proton donor acceptors.
The Brunstad-Lowry definition, yeah. An acid donates a proton, H+, a base accepts one. We talk about strong acids like HCl, which fully dissociate in water, giving them a low pK, and weak acids like acetic acid, which only partially dissociate, having higher pPa values.
And for acids with multiple protons, like H3PO4.
Those are polyprotic acids. Each successive proton removal becomes harder. It's tougher to pull a proton off H2PO4 than off neutral H3PO4, and even tougher to pull one off HPO4 too because of the increasing negative charge. So the pKa values increase significantly.
What actually makes an acid strong or weak in solution? Is it just about the bond strength?
Gas phase proton affinity matters, but in solution, especially water, solvation is hugely important. How well does the solvent stabilize the ions formed? The Born equation shows that small, highly charged ions are very strongly stabilized by polar solvents like water.
So water helps pull the proton off.
It helps stabilize the resulting anion, which pulls the equilibrium towards dissociation, making the acid effectively stronger in solution. This also leads to the leveling effect.
Ah, the leveling effect, meaning you can't tell the difference between really strong acids and water.
Exactly. Any acid stronger than H3O+ will just react completely with water to form H3O+. So H3O+ becomes the strongest effective acid in water. Similarly, any base stronger than OH will just react to form OH, making hydroxide the strongest effective base. The solvent sets the window of observable acid-base strengths.
Are there predictable trends in acidity, say for metal ions in water?
Yes. Metal ions surrounded by water molecules are called aqua acids. Their acidity increases as the metal ion's positive charge increases and its ionic radius decreases.
Higher charge density pulls electrons better.
Right. It polarizes the OH bonds on the coordinated water molecules more strongly, making it easier for a proton to leave. So F3 plus AQ is a much stronger acid than F2 plus AQ.
What about oxoacids like sulfuric or nitric acid?
For those, Pauling gave us some useful rules of thumb. The pK depends mainly on the number of non-hydroxyl oxygen atoms attached to the central atom. More oxygens pull electron density away, stabilize the anion, and make the acid stronger.
Useful rules. And some things can be both acids and bases.
That's amphoterism, common for oxides of elements near the metal-nonmetal dividing line, like aluminum oxide, Al2O3, which reacts with both acids and bases.
But you mentioned earlier that the Lewis definition is often more useful in inorganic chemistry.
Definitely. Lewis acids are electron pair acceptors. Lewis bases are electron pair donors. This is much broader. A proton is a Lewis acid, but so is BF3 or LCl3 or any metal cation. Water, ammonia, chloride ions, they're all Lewis bases, ligands.
This covers coordination chemistry.
Fundamentally, yes. Metal ligand bonding is Lewis acid-base interaction. Even things you might not expect, like iodine, I2. It can act as a mild Lewis acid, accepting electron density from a donor solvent into its low-lying antibonding orbital.
That explains those color changes, like iodine and hexane versus ethanol.
It contributes to it, yes. The interaction changes the electronic transition.
And we categorize these Lewis acids and bases.
We use the hard and soft acids and bases, HSAB principle. Hard means small, non-polarizable, like H plus Li plus F. Soft means larger, more polarizable, like Ag plus AiCO. The principle states that hard acids prefer to bind to hard bases and soft acids prefer soft bases. It's qualitative, but very useful.
Like predicts why silver prefers iodide over fluoride.
Exactly. For more quantitative predictions, there's the Drago-Wayland equation, using parameters E and C for electrostatic and covalent contributions to predict adduct formation enthalpies.
Okay, powerful concept. So let's switch to the other major reaction type, oxidation reduction or redox.
Electron transfer reactions. Oxidation is loss of electrons, reduction is gain of electrons. We use oxidation numbers to keep track.
Bookkeeping system.
Sort of, yeah. Assigning hypothetical charges based on electronegativity rules. Balancing redox reactions can be tricky. Needing a systematic approach to balance atoms, charge, electrons, often using H plus and H2O in aqueous solutions.
How do we know if a redox reaction will actually happen spontaneously?
That's where standard electrode potentials, E degree, come in. These measure the tendency for a half reaction to occur as a reduction relative to the standard hydrogen electrode.
So we combine half reaction.
Right, you combine the reduction half reaction and the oxidation half reaction, reversing one of the tabulated reductions. If the overall cell potential E degree, cell equals E degree oxidation is positive, the reaction is thermodynamically favorable under standard conditions. Gibbs free energy change is negative.
Useful for predicting reactions, designing batteries, fuel cells.
Absolutely vital. The electrochemical series ranks species by their oxidizing-reducing strength based on their E degree values. And the Nernst equation lets us calculate the potential under non-standard conditions, taking concentrations into account.
What about water itself? Can it react in redox?
Oh yes, water is actually quite stable, but it can be oxidized to O2 requires strong oxidants like C3+, or reduced to H2 requires strong reductants like sodium metal.
But these reactions aren't always fast.
Often not, especially water oxidation. Forming the OO bond has a significant kinetic barrier called overpotential. This means you often need a substantially higher potential than theoretically predicted by E degrees to make the reaction happen at a reasonable rate. This is actually crucial industrially.
How so?
In the chlor-alkali process, making chlorine gas by electrolyzing brine, NaCl solution, you want to oxidize Cl to Cl2. Water oxidation to O2 is actually thermodynamically easier, but its high overpotential on typical electrodes allows the desired chlorine production to dominate. Kinetics wins.
Clever chemistry. You mentioned diagrams for visualizing stability earlier too. Latimer, Frost, Pourbaix diagrams.
Yes, really helpful tools. Latimer diagrams just list the standard potentials connecting various oxidation states of an element in a line. They're good for quickly spotting species prone to disproportionation.
It's proportionation, reacting with itself.
Exactly. An intermediate oxidation state reacting to form both a higher and a lower state. If the potential on the right of a species in a Latimer diagram is higher than the potential on its left, it's thermodynamically unstable to disproportionation, like hydrogen peroxide in acid.
Okay. What about Frost diagrams?
Frost diagrams plot a function of potential, and AE degrees, against oxidation number N. The lowest point on the plot represents the most stable oxidation state under those conditions, usually pH 0 or pH 14. Steeper slopes between points indicate higher potentials for that redox couple. Unstable species sit above the line connecting their neighbors makes disproportionation tendency visually obvious.
More graphical. And Pourbaix diagrams added pH.
Yes, Pourbaix diagrams are 2D maps showing the thermodynamically stable form of an element, ion, solid oxide, etc., as a function of both potential and pH. Incredibly useful for corrosion, geology, environmental science, understanding how iron behaves in lakes, for example.
Seeing the stability field, can these redox ideas be used industrially, like for getting metals from ore?
Absolutely. That's where Ellingham diagrams come in. They plot the Gibbs free energy of formation of oxides per mole of O2 versus temperature.
Gibbs energy versus T.
Right. Since G = HT, and forming an oxide usually involves consuming gas, O2, the entropy change is often negative, making the line slope upwards. The lower a line on the diagram, the more stable the oxide.
So how do you use it for extraction?
You look for a reducing agent, like carbon or carbon monoxide, which also have lines on the diagram, whose oxide formation line lies below the metal oxide line at a given temperature. This means the carbon reaction has a more negative edge, and it can thermodynamically reduce the metal oxide.
So you can find the minimum temperature needed for reduction.
Exactly. It shows why you need very high temperatures in a blast furnace to reduce iron oxides with carbon CO, and even higher temperatures to reduce silicon dioxide.
But some metals are too reactive for this.
Yes, highly electropositive metals like aluminum or sodium, their oxide lines are very low on the Ellingham diagram. For them, you need electrochemical extraction electrolysis using electrical energy to force the non-spontaneous reduction, like the Hall-Héroult process for aluminum.
Fascinating application of thermodynamics. Okay, final stretch. How do chemists actually figure all this stuff out? The tools of the trade, symmetry plays a big role first, right? Chapter 6?
Yes, molecular symmetry is a really powerful concept. We describe a molecule's symmetry using symmetry elements like rotation axes, Cn, mirror planes, sigma, and inversion center. The complete set of symmetry operations for a molecule defines its point group.
Like tetrahedral or octahedral.
Exactly. And the properties of these point groups are summarized mathematically in character tables.
Character tables look intimidating. What are they actually used for?
They are incredibly useful. They help us classify molecular vibrations, for instance. We can predict which vibrations will absorb infrared light, IR active, and which will scatter light differently in Raman spectroscopy, Raman active.
How does that help?
It helps identify molecules. For example, in a molecule with a center of inversion, centrosymmetric, the exclusion rule states that no vibration can be both IR and Raman active. This can help distinguish isomers, like cis versus trans-square planar complexes. The trans isomer is often centrosymmetric, the cis is not.
Oh, a practical diagnostic tool. What else?
Character tables are absolutely essential for understanding molecular orbital theory in a more rigorous way. They help us construct symmetry-adapted linear combinations, or SALCs, of atomic orbitals, basically. The right combinations of atomic orbitals that can mix to form molecular orbitals.
Group theory underpinning MO theory.
Okay.
Moving to Chapter 7, coordination chemistry. Metal ions plus ligands.
A huge area of inorganic chemistry. These are complexes where a central metal atom or ion acting as a Lewis acid is bonded to surrounding molecules or ions called ligands, which act as Lewis bases, donating electron pairs.
And Alfred Werner figured out the basics.
He did heroic work, established that complexes have definite geometries like octahedral or square planar, and pioneered the study of isomerism in these compounds.
Isomerism, same formula, different structure. What kinds are important here?
Lots. Linkage isomerism, where an ambidentate ligand like nitrite, NO2, can bind through either the N or an O atom. Ionization isomerism, where a ligand and a counterion swap places. Hydrate isomerism, involving water. And then stereoisomerism, geometrical isomers like cis-trans and square planar, or FACMR and octahedral.
Cis-trans is opposite adjacent. FACMR is.
In an octahedral Ma3b3 complex, FAC, facial, means the three identical ligands occupy the corners of one triangular face of the octahedron. Mer, meridional, means they lie along a meridian, like the equator plus one pole. And importantly, optical isomers or enantiomers, non-superimposable mirror images, often found in chiral octahedral complexes.
Lots of structural possibilities. How stable are these complexes?
We quantify their stability in solution using formation constants, Kf, which measure the equilibrium for complex formation. A key factor influencing stability is the Chelite effect.
The Chelite effect. Ligands that bite more than once.
Exactly. Polydentate ligands, or chelating ligands, which can bind to the metal ion through multiple donor atoms like ethylenediamine and binding through two N atoms, form much more stable complexes than analogous monodentate ligands, like ammonia NH3.
Why is that?
It's largely an entropy effect. When several monodentate ligands are replaced by one polydentate ligand, the number of free molecules in solution increases, leading to a favorable increase in entropy. There's also the macrocyclic effect. Pre-organized cyclic ligands bind even more strongly, often with an added enthalpic benefit.
Makes sense. Okay, finally, Chapter 8. The inorganic chemist's actual toolkit. How do we see these structures and probe these reactions?
A vast array, but let's hit the highlights. For determining solid-state structures, atom positions diffraction methods are king.
X-ray diffraction.
Primarily X-ray diffraction. When X-rays hit a crystal, they diffract off the electron clouds of the atoms. Bragg's law relates the diffraction angle, wavelength, and the spacing between atomic planes in the crystal.
So you get a pattern that reveals the structure.
Exactly. Pattern X-ray diffraction is great for identifying known crystalline phases. But single crystal X-ray diffraction can give you a precise 3D map of electron density, allowing you to pinpoint atom locations and measure bond lengths and angles with incredible accuracy. It's the gold standard for structure proof.
What about finding light atoms like hydrogen?
X-rays scatter off electrons, so light atoms are hard to see. Neutron diffraction is better for that, as neutrons scatter off nuclei, and sensitivity isn't so dependent on atomic number.
Okay, that's structure. What about energy levels, bonding, vibrations?
That's where spectroscopy comes in. Absorption spectroscopy measures how much light is absorbed at different wavelengths. UV visible spectroscopy probes electronic transitions, often between d-orbitals in transition metal complexes. That's why they're often brightly colored.
The source of color. And IR and Raman.
Infrared, IR, and Raman spectroscopy both probe molecular vibrations. IR measures absorption of infrared light when a vibration causes a change in the molecule's dipole moment. Raman measures scattering of light when a vibration causes a change in the molecule's polarizability.
Complementary techniques.
Often, yes, especially due to symmetry rules like the exclusion rule we mentioned. They give you a fingerprint of the functional groups present and information about bonding. For example, the stretching frequency of a carbon monoxide ligand, CO, tells you if it's terminally bonded to one metal or bridging between two.
Very informative. What about magnetic properties or nuclei?
Resonance techniques are powerful. Nuclear magnetic resonance, NMR, is huge. It probes the magnetic environments of specific nuclei, like 1H, 13C, 31P, and 19F. It gives incredibly detailed structural information, can reveal dynamic processes like fluxionality.
Molecules changing shape fast.
Yeah, NMR can often see that. And coupling patterns between nuclei give geometric information distinguishing isomers, for example. Electron paramagnetic resonance, EPR, sometimes called ESR, is similar but detects species with unpaired electrons.
So useful for radicals or many transition metal complexes.
Exactly. And then there's mass spectrometry, which measures the mass-to-charge ratio of ions. It gives you the molecular mass, characteristic fragmentation patterns, and even isotopic information, like seeing the distinct pattern for bromine isotopes in a molecule containing bromine.
Identifying the pieces.
Yeah.
And elemental analysis.
Crucial for confirming composition. Classic CHN analysis for organic content, or techniques like X-ray fluorescence, XRF, for a broader range of elements. Thermal analysis, TGA, DSC, watches how materials change upon heating decomposition, phase transitions. And magnetometry directly measures magnetic susceptibility to determine the number of unpaired electrons.
An amazing array of tools to probe the inorganic world. Wow, okay, we have really journeyed through a lot. From the birth of elements in stars right down to the quantum rules governing electrons.
How they bond to make molecules with specific shapes.
How those molecules pack into solids, the energy involved.
And the fundamental reactions, acids, bases, redox that drive chemical change.
Plus a peek into the incredible toolkit chemists use every single day to figure all this out.
And the key takeaway is that these foundations aren't just separate topics, they're deeply interconnected. Quantum mechanics explains bonding, bonding explains structure, structure and bonding explain reactivity. It all builds.
It forms a coherent lens, as you said earlier.
Exactly. A lens to interpret the whole vast, varied world of inorganic chemistry. Mastering these core ideas really equips you with the framework to understand chemical behavior, maybe even predict it, from simple salts to complex catalysts or materials.
So what does this all mean for you listening? Think about the materials around you. Your phone screen, the battery inside it, the paint on a car, the catalyst cleaning its exhaust.
Even the enzymes in your body using metal ions.
Right. How many of these foundational principles, electron configurations, bonding types, structures, redox potentials, are constantly at play in their existence and behavior? It's all around us, waiting for you to deep dive further.
Keep that curiosity going.
Absolutely. Thank you so much for joining us on this deep dive into the foundations of inorganic chemistry. Keep asking those why questions, keep exploring, and we'll catch you next time for more chemistry insights.